All right. Now we've already talked about all the units, so what we're going to do is we're going to take delta G is equal to a negative NFE, which is, so the number of moles of electrons is 2. I've got 2 moles of electrons that I'm transferring one metal to the other. My Faraday constant is 96,485, and my volts, my E, is 1.1 volts. That is going to be 212,000 joules per mole. But remember, if we want to calculate delta G, we really need that in kilojoules per mole. And so that's what I'm going to do there. All right. So now what we're going to do is we're going to use delta G to calculate K. And we know that delta G is equal to the negative RT log of K. And I'm just going to plug everything in, a negative 212. Here's again another reason why we need to put this in kilojoules. 212 is equal to R, a negative R. Remember, we have to put R. R is also in joules. We're going to put it in kilojoules. 8314, I did that correctly this time, times our temperature, which is 298. Times the log of K. So that means that in this case, log of K is equal to 85.57. Remember that I take each side and do that. And when I do that, I get log of K is equal to e to the, log of K is equal to log of K, e to the log of K is equal to K. So I get K is equal to e to the 85.57, which is 1.5 times 10 to the 37. That is a really, that kind of went off this thing here. Really large K. So what I was able to do is I was able, through all of these three equations, I was able to go from E to delta G to K. And so there's a way that we can show this, and I'm going to write this here. Let me pull all this over here. I'm going to put it over here in this corner. All of the equations are related to each other. And so I can say, okay, delta G is here. If I want to go to K, I can use delta G is equal to negative RT log of K. If I want to go from delta G to E, I can do that. This one would be delta G is equal to NFE. And if I want to go from here to here, I'm going to use E is equal to RT divided by NF times the log of K, which is going to be a combination of both of those. So all of these are related to each other. Okay, now when we did all of those reactions, we did those under standard conditions, room temperature, 1 atmosphere, and 1 molar. But sometimes the concentrations in our half cells of our solutions are not 1 molar. And so what we have to remember is that, first of all, before we do that, is that, and people have asked me this a lot all day, because you all already are thinking about this, you're all ahead of the game. You realize that as a cell runs and the concentration decreases of the reactants and the concentration of the products increases. So everyone's been saying, so what happens to our battery? When will it run out? So that's what we want to look at next. As the cell runs progressively, it decreases over time, the voltage does, right? Because we're going to equilibrium. And equilibrium is where we have 0 volts and the value of G becomes 0. The reason for that is because where we used to have a hill between the anode and the cathode, we don't anymore. There's nothing driving the reaction. Everything is basically run out. Okay, now there's an equation in your formula chart. So we've talked about both of these now. We're down to, I'm going to do this one next and then this one. It's called the Nernst equation. Now you are not going to ever have to calculate anything with this equation at all, but you are going to have to understand conceptually what it means. Because as soon as we start changing the concentrations of our solutions in our cells from 1 mole per liter and being equal, we start having to deal with Q. Because remember, this is an equilibrium situation. So Q is going to be a part of this. And basically, we're just going to look at it in these terms. We're going to find that if Q is less than 1, that makes this whole thing negative. So E minus a negative is E plus something. So our E goes up if I change my concentrations to where Q is less than 1. If I change my concentrations to where Q is greater than 1, then this remains positive, and I have E minus some positive number, and so my voltage is going to go down. Okay? So that's all you have to know for the Nernst equation, and that's what this is kind of about. We're going to use at equilibrium, our potential is 0. Now at standard cell potential, everything is equal to 1 because Q is products over reactants. If all the molar concentrations are 1, it's 1 divided by 1. However, then when the system approaches equilibrium, Q gets close to K and the cell stops performing. What we're going to look at now is deviations from standard conditions where Q is greater than 1 or Q is smaller than 1. Okay? So let's do that next. Now, here's our zinc copper cells, right? And we're going to look at it first here under standard conditions. So under standard conditions, all of our species, and let me put up here, I'm going to put this up here so that we can refer to it. RT over T times ln of Q. Of course, all we care about is whether this is a positive number or a negative number. That's all we care about. So if we look at this system where we're under standard conditions, Q is just going to be 1 times 1 divided by 1 times 1 or 1. We already know the voltage of this. Now it turns out K is very high for this because it sits very far to the side of the products. As the cell runs its course, this becomes 0. This, of course, becomes 0. And then I reach equilibrium, so my Q at equilibrium is K, which is here. Okay, now let's look at what happens when our concentrations are not at 1 molar. Let's say we start with 10 molar copper, 1 molar zinc. If I put that into my Q equation, that would be 1 divided by 10. And so, sorry about that interruption. And so that becomes 0.1. I run my voltage, I find, look at that. My voltage has gone up from 1.10 to 1.13. Why is that? Well, in this case, Q is less than 1. And if we remember, when Q is less than 1, the log is always negative, which is a negative minus a negative number is plus. So it's my original value plus this little bit makes my cell go up. and it did. If I do this, if I continue to dilute it, and I have my Q at 0.01, it goes up even farther. All right, let's look at the opposite direction. In this case, I'm going to make my zinc concentration high. So what's going to happen is I'm going to get 10 divided by 1, or 10. When I do that, let's go back up to our equation. The log of a integer is always positive. So now what's happening, I'm going to take my original value of 1.1 volts, and I'm going to subtract a positive number, which is going to make my cell value go down. And sure enough, that's what happens. When this is 10, my voltage goes to 1.07, and if I increase the concentration even more, it goes to 1.04. So this is conceptually what you need to do. You need to be able to remember that the log of a number less than 1 is negative. The log of a number greater than 1 is positive. If I put a negative value in here, that means I'm adding, because a negative times a negative, I'm adding to my original cell, it goes up. If my Q is greater than 1, if it becomes positive, that means I'm subtracting, and my cell voltage goes down. So, in summary, all this says, when Q is less than 1, E is greater than the original E. When Q is greater than 1, E is less than regular E. And that's all you have to know about that Nernst equation. So I'm going to go ahead, stop this video, and we have one more short concept we're going to look at, and then we'll be done with the whole unit.